All the details can be found in 2 preprints that are currently up on the archive. So a brief outline, I'll start with just talking about what is the power asymmetry. Why would we ever want to create such a thing? And I'll review some of the observational evidence that motivates us. And then how you can get a cosmic power asymmetry from superhorizon perturbations. Now that's going to lead us to a bit of a segue, because the minute you start postulating superhorizon perturbations, you need to worry about their direct consequences on the cosmic microwave background. So that'll lead us to the second part here, superhorizon perturbations in the cosmic microwave background. We'll look at the signatures that these things have on the CMB directly, in addition to the cosmic power asymmetry. That'll lead us to some bad news, and will force us to consider an alternative theory of inflation called the Curvaton model. And I'll talk about what went wrong with our original proposal and how the Curvaton model fixes it. And I'll also include a brief review of the Curvaton model of inflation. Finally, we'll see if power asymmetry from the Curvaton does work. I'll review some of the existing constraints and then some of the future predictions that this model makes. So when I talk about a cosmic power asymmetry, what I mean is considering the CMB as a Gaussian field with isotropic power times a dipolar modulation. So we have a dipole structure here and then some modulation amplitude. And what that does is it takes the isotropic map, so this is the S of n here, and revs up the amplitude with this dipolar modulation. So you end up with bumpier perturbations on one half of the sky and a smoother sky on the other half. Now, of course, this looks absolutely bizarre. And of course, we've seen WMAP, and we know that this is not what WMAP looks like. But this is an extreme asymmetry. This is a 50% asymmetry. What if it were just a 10% asymmetry? Then it becomes a lot more difficult to see with the naked eye, and you need to do some statistics. So this leaves the open question, is our universe isotropic or asymmetric? And the asymmetry was originally found, 2 papers, Erickcek, Hansen et al., in 2004 in the WMAP first-year data. They looked for it and found it in regions of L between 5 and 40. And this shows their primary result. What they did was they divided the sky in half and analyzed the power independently in the 2 hemispheres, and then took the ratio of the power between those hemispheres. And so these colored disks here, from yellow to red, show low to high ratio of power in the 2 hemispheres where the pole is centered at this disk. And you can see there's a smooth dipolar structure, that this ratio is maximized when your top hemisphere is located somewhere around here, and minimized when your hemisphere is located somewhere around here. And you can see it's smooth, which means that this is a broad hemispherical asymmetry. It's not one specific point. Another way to see that is if you look at which one of these little disks has abnormally high power compared to what you'd expect from a Gaussian simulation, i.e. greater than 80%, and which ones have abnormally low power. And you can see the abnormally low power ones are clustered more in this side of the sky, and the high ones are clustered more on this side of the sky. So again, we see this is not a local, it's more of a dipolar structure like I said before. The power asymmetry is maximized when the equatorial plane divided into the 2 hemispheres is tilted with respect to the galactic plane. And only about less than 1% of simulated isotropic maps have a 2 hemisphere split with this much asymmetry. So I'll talk mostly in this language. In terms of the ratio, it's about 1.5. But I'll talk about A, and we'll see A is about 12% here. So this is the exact model I mentioned before. You have the observed CMB temperature, a Gaussian field with the modulation, and we're fitting likelihood contours here for A. This is using WMAP3 data, subsequent analysis by the same group. And what you see here, this is the likelihood as a function of A, and for 2 different sky cuts and 4 different frequencies. And you can see that the likelihood is not peaked at A equals 0, as we would expect for an isotropic universe. Instead, it's peaked at about 12%.
So A is not a random field. A is just pure dipole pattern.
A is just a modulation amplitude parameter, so it's fixed. And so what you're doing is you're multiplying the random field by 1 plus A to rev up the amplitude of the fluctuations. And the probability of measuring this large of an amplitude with if the background were actually 0 is about 1%. So again, we're at about the 99% confidence level.
So which scales dominate this?
So it was looked for and found in L between 5 and 40. Some subsequent analyses have looked at higher L. The results have been a little less conclusive. I'll talk about that later. But it's known to exist between L and 5, L equals 5 and L equals 40. So the asymmetry is rather difficult to explain with foregrounds, largely because it's present in all colors. As you can see here, it's basically the same for the 3 frequency bands and the linear combination. It's also not aligned with the galaxy, as we would expect foregrounds to be. It's also difficult to explain with WMAP systematics because Kobe actually saw the exact same thing, albeit at lower statistical significance because of the larger error bars. So how do we propose to create this asymmetry? In the standard picture of inflation, the way you get these fluctuations is you have a uniform background of the inflaton field, phi, and then you get little quantum fluctuations on top of it. But if we're here at the center, we look out to the cosmic microwave background, shown here as the blue circle, and we see about the same amplitude of fluctuations on both sides of the sky. However, the amplitude of those fluctuations, here we have the power spectrum for a normal conformal Newtonian metric. The power spectrum here is dependent on the background value itself. So our idea was to put in a large superhorizon fluctuation that effectively changes the mean value of the inflaton field on one side of our sky as opposed to the other, and that will in turn change the amplitude of the fluctuations. So we call this large amplitude superhorizon fluctuation the supermode as a nickname. Now, we saw the modulation amplitude here is 12%. That translates to a power asymmetry of about 20%, that the power asymmetry is 20% higher and 20% lower on opposite hemispheres. Generating this much asymmetry requires a very, very big supermode, largely because of 2 related characteristics of the inflaton field. Perturbations with different wavelengths are very weakly coupled in inflation. And the fluctuation power is not very sensitive to the background field. This is how we always end up with n sub s about equal to 1 in inflation. And sure enough, if you calculate how the power depends on the background value, it's suppressed by a factor of 1 minus n sub s. So this is really small. If we want a power asymmetry of 0.2, we're going to need delta phi to be very large.
And it's not dynamical, we just put it by hand. It's not supported by dynamical equations. This construction.
The supermode?
Yeah.
No.
I mean, you put it in by hand, but you can solve its dynamics. I mean,
No, it's not, because it's a de Sitter background. And this mode it will be immediately stretched out if you let it live for a couple of defaults.
right, right. But we're looking at
This is why I'm saying it's not dynamical. You just put it by hand and you don't know what is the reason to keep it like that.
oh, you're right, right. No, it would be immediately stretched out. And so I'll talk a bit later about the origins of the supermode and what we think about that. The immediate concern, though, is given that you have this large-scale perturbation in phi, that's going to directly induce a large-scale potential perturbation. And those large-scale potential perturbations lead to CMB temperature anisotropies directly through the Grishov-Zeldovich effect. And so you would think that if the energy on one side of our universe is bigger than the energy on the other side, we would see a very large CMB dipole. And that would be ruled out by observations. So that brings me to part 2 here, and considering superhorizon perturbations in the cosmic microwave background and what signatures you would expect to see in the CMB from such a perturbation. So I mentioned the dipole. But the thing about the dipole is that it sometimes cancels. It's been known to cancel in an Einstein de Sitter universe since the 70s. And the way that works is if you have a superhorizon potential perturbation, it can be approximated as just a linear gradient in the potential by some constant amplitude. And you end up with a Sachs-Wolf dipole that's just 1/3 of the potential. So the photons that have to climb out of the well get redshifted, the photons that fall in get blue shifted. But we are also falling in this potential well. And that gives us a Doppler dipole due to our motion relative to the photons emitted at the surface of last scattering. Now this is Einstein de Sitter universe, which means everything is nice and analytic in a theorist's dream. So the formula for the velocity is very, very simple. And the key here I want to point out is that due to the factoring out of the distance to the surface of last scattering, x decoupling here, the impact of the velocity is inversely proportional to the distance of last scattering. Also, the co-moving distance in Einstein de Sitter is nice and analytic and simple. And when you calculate the Doppler dipole, you end up with a very nice cancellation of these two terms and a cancellation of the two, and you're just left with minus 1/3, which will exactly cancel the Sachs-Wolf dipole. So in an Einstein de Sitter universe, superhorizon perturbation generates absolutely no dipole, because also, since psi is constant, there is no ISW effect. So this is the complete picture. Well, that's really nice, and it's very simple, but our situation in a lambda CDM universe with radiation is much more complicated. And even in the very early literature on this, it was said kind of cavalierly, well, surely this cancellation won't go through once we put in a cosmological constant. So we set out to test that idea. The main difference between our universe and an Einstein de Sitter universe, for our purposes here, is that in our universe, psi, the potential, evolves. It starts out at its primordial value and then decays to 9/10 its primordial value as the universe transitions from radiation domination to matter domination, and then it falls off rapidly as lambda comes into play and becomes more important. And that affects our dipole calculation in 3 ways. First of all, the radiation at decoupling means that here at decoupling, the field wasn't exactly 9/10 of its primordial value. It was a little larger.
But this is of course an Einstein de Sitter as well, right?
No, this is for lambda CDM with
No, but
radiation.
this transition first, lambda CDM is at the end. This first transition occurs in Einstein.
Right, but Einstein de Sitter technically is just matter, not even radiation, to be purely Einstein de Sitter. So in pure Einstein de Sitter, you assume, that previous calculation assumed that there was no radiation at decoupling. So radiation at decoupling increases the Sachs-Wolf effect due to the fact that the potential is a little bit larger than we used before to get that factor of 1/3. So instead of 1/3, we get about 0.4. Lambda comes into this mainly through the distance to the surface of last scattering. It reduces the Doppler dipole that way. It also introduces an ISW effect. Then you can see that the signs here are kind of interesting. We've increased the Sachs-Wolf effect, and we've reduced the Doppler dipole relative to what we had before. So now we can see that the Sachs-Wolf effect is not going to be perfectly canceled. But now we have an integrated Sachs-Wolf effect that's negative that could come in and pick up the slack.
Can you a little bit explain once again this point 4, the very first point?
Yeah.
What formula do you use to get it?
So that comes from, in the normal calculation for Sachs-Wolf effect, you have that the primordial temperature is, the temperature perturbation at decoupling is related to psi. And it's related to psi at decoupling minus 3/2 its primordial value. And the way you derive that 1/3 that's so often used is you stick in that primordial value is 10/9 the value at decoupling. And if it's not 10/9 exactly like it isn't here, then that changes this number slightly. So it just changes the relationship that enters in the Sachs-Wolf effect from the primordial to the relation at decoupling. I'll go over I'll talk about it in the office. But yeah, it just has to do with the way that constant is set there, and the relationship between its primordial value and its value at decoupling.
You know, the value of the decoupling actually doesn't enter the function. It is the value of the plateau on which the particle is found.
Oh, to get the Sachs-Wolf effect, you're looking at the surface of black scattering. So the temperature anisotropy is going to be still proportional to the superhorizon mode evaluated at the surface of black scattering. And this delta 1 here includes Sachs-Wolf, Doppler, and integrated Sachs-Wolf anisotropies. And when you look at it, you find something rather surprising. So here I've plotted this delta 1 parameter for both situations that include radiation and situations that do not include radiation, but all include lambda. And what you find is that the sum of the Sachs-Wolf and the Doppler effect and the sum and the ISW effect exactly cancel in all cases. So the three cosmological parameters that enter here are omega matter, the redshift of matter radiation equality, and the redshift of decoupling. And for instance, Einstein de Sitter is right here in the blue, no radiation, omega matter equals 1. And in that case, the Sachs-Wolf and Doppler cancel, and there is no ISW. As you dial down omega matter, the cancellation is no longer perfect, but it's directly canceled by the ISW. It always sums to 0, no matter what you do. So the dipole cancels for all flat lambda CDM universes, even if radiation is included. This was a little surprising to us. We found here that for adiabatic perturbations, they cancel in flat universes that contain matter, radiation, and a cosmological constant. We started to wonder, is this something special about matter and radiation? What if there's something else? So we just proposed a quick toy model, considering a universe with some exotic fluid with some equation of state greater than 1/3, so it dominates the early universe, and a cosmological constant. And we found that for this toy model, sure indeed, the dipole terms still cancel for adiabatic perturbations. So now we're really intrigued and think there must be a deeper reason going on here. And some of the reasoning we came up with has to do with this special synchronous gauge that exists for any single observer. It's kind of an analog of Riemann normal coordinates. For any one observer, you can find a special synchronous gauge where the metric is Friedman-Robertson-Walker plus corrections that are ordered k². And in synchronous gauge, galaxies don't have any peculiar velocity by definition, so you have no Doppler effect for a co-moving observer. And then there's no order k temperature anisotropies because there's no terms in the metric of that order, there's no Doppler dipole, and since this is an observable, it's kind of expected now that maybe these terms always cancel as a gauge argument. So given that you don't have a dipole, you have to go beyond the dipole to start constraining these superhorizon modes. And so now our approximation before of this superhorizon mode as a single linear gradient won't work. We're going to approximate it as a sine wave with some arbitrary phase at our location. And then we expand the temperature anisotropy in powers of k dot x, where x is the distance to the surface of last scattering. And you can work out an expansion in higher orders of those terms. Now, we've already seen that the dipole term is gone, but we're left with the quadrupole and octupole term that we want to translate into multiple moments, ALM. And we're going to be working in a frame where the z-axis is aligned with the asymmetry and aligned with the superhorizon mode defined by this k value. When you do that, yeah?
I was just wondering, going back to your previous argument, is another way to say why it always cancels that just in GR I can transform to a frame where the gravitational field vanishes, but I can't transform to a frame where the tidal field vanishes?
Exactly. It's a very close analogy to Riemann normal coordinates, which is exactly what you're talking about. So it's kind of the cosmological analog to Riemann normal coordinates. Exactly. Now
so you cancel it for pure gradient, right?
Right.
For
But
gradient.
so all that is it's a cancellation of the terms, no matter what, if you use this form or a pure gradient, either one, the terms that are linear in k always cancel.
Well, in a sense, it's not physical mode.
So the multiple moments here, you still get a residual L equals 1 multiple moment. It comes from the octupole term because it's quadratic in kx. That means it's comparable to the L equals 3 octupole moment. And since our dipole is contaminated by our proper motion, this is going to give us a less restrictive constraint. The two constraints we have to worry about are the quadrupole, A20, and the octupole, A30. And the quadrupole is generally going to be the more strict constraint because it's proportional to kx squared, whereas the octupole is proportional to kx cubed. And remember, the kx is a small quantity. So looking at the quadrupole constraint, we might remember the motivation here. We wanted to introduce a superhorizon fluctuation in phi to get the power asymmetry. We also wanted to introduce, we were worried that the superhorizon perturbation would induce a potential gradient, would induce temperature fluctuations. What we really want to constrain is this quantity delta psi, which is the variation of psi across the observable universe between us and the surface of last scattering. That's going to be proportional to kx itself and the phase of our position. So the quadrupole constraint comes in here, and its upper bound is determined by the maximum allowed quadrupole moment that is aligned with the supermode. Now, this isn't the measured quadrupole moment, because the measured quadrupole moment includes contributions from all different scales of perturbations. And it's possible that those other scales could cancel this one out and mask it slightly. So the conservative upper bound on the maximum allowed quadrupole aligned with the asymmetry is just 3 times the root mean squared variance for the quadrupole moment. And so that's what we use as our upper bound. Now the key thing about this constraint is its dependence on the phase. You can see here the quadrupole is dependent on sine omega, which is the phase of our location. And that means that this quadrupole constraint vanishes. If we are located right at the 0 point of the sine wave, as I've drawn it here, there is no quadrupole. So maybe that's how we can evade this constraint. That leads us to the octupole constraint, which, like I said, you expect to be weaker. But since the quadrupole can vanish, we have to look at it anyway. Again, we constrain it in the same way, looking at 3 times the root mean squared variance in the octupole moment. But here the key difference is that both the octupole and the thing we're trying to constrain has the same dependence on our position. So that dependence cancels out. And the octupole constraint, it doesn't matter where we sit on this wave. The octupole constraint is always the same. And it's actually a pretty strict constraint. We could hope to evade it by just decreasing kx, stretching the wave out. Then we could keep our needed delta psi and still satisfy this constraint. But as an aesthetic choice, we also wanted linearity beyond horizon. We didn't want this to be a sign of nonlinear structure, just looking outside of our view. We wanted this to be a superhorizon perturbation, not a superhorizon mountain. And when you add that constraint, that we wanted this whole perturbation everywhere to be less than 1, that puts an upper bound on delta psi directly in terms of kx. And when you combine these 2 bounds, you end up with a very strict and impossible to escape bound on delta psi that's very, very small. And remember that our power asymmetry that we were going to create is directly proportional to delta phi. The inflaton is directly proportional to delta psi, and that means that this bound translates directly onto the power asymmetry, and it's less than 1%. And remember, the observed asymmetry was 20%. So that's way too big to be explained by this mechanism.
Yeah, but you use a particular form of the supermode.
We just used a sine.
If you change its profile.
Well, you mean if it's not a sine wave?
That's right.
So as long as one way you could evade this constraint is exactly like you're saying. If you're willing to make it just a linear gradient and not worry about its turnaround, if you're willing to just have it stretch across the horizon and not worry about the fact that it's going to exceed 1 somewhere, it's going to bottom out at 0 somewhere, and you end up with us on the hillside of a mountain. Then you can evade that constraint.
Well, that could happen far outside the horizon, anyway, right?
This is true. It's kind of an aesthetic argument about we wanted to do this with the superhorizon perturbation, not with something that extreme.
No, but if it is not really a function of KS, you always have an expansion with KS.
Mm-hmm. You always have an expansion of KS.
Sense,
the question is...
And different terms contribute to different health, right?
Right.
Well, the critical issue is what is the spectrum of the low K?
Spectrum, yes.
Yes.
And that is what's going to determine what Lev is talking about. And what they've been dealing with is that there would have to be not just, I mean, it's better to deal with the spectrum than a single K mode.
That's no, absolutely.
But you also have to then, if you want to do their thing, you have to do a lot of phase coherence among the Ks in order to
get a structure. Exactly.
And in particular, the critical issue is bleed into other modes.
Mm-hmm. So this type of approach, this type of calculation, you could do the exact same thing, apply the exact same constraints, apply the exact same formalism, and start out with a different functional form for the supermode. And it would go through in pretty much the same way. So this trouble with our original model is what led us to consider the Curvaton scenario. So the Curvaton scenario for inflation has been around for quite a while now, over 10 years. Here's some of the original papers. There are many, many others. And what the Curvaton helps us with is that the problem with the inflaton model kind of had two sides to it that were related. The fluctuation power was only very weakly dependent on the background value. So it was suppressed by this 1 minus n sub s. And that meant that the small power asymmetry that we observed required a very, very large fluctuation in phi. The other problem that we had with the inflaton model is that the inflaton dominates the energy density of the universe, which means if you change the inflaton value, it's going to create a huge potential perturbation. And that constraint on the potential perturbation leads back to a constraint on the power asymmetry with absolutely no wiggle room. The solution. What if the primordial fluctuations could be generated by a subdominant scalar field, aka the Curvaton? Then we'll see that the fluctuation power depends more strongly on the background Curvaton value. And then the CMB constraints on delta psi do not directly constrain the power asymmetry. There's a new free parameter, which is the fraction of energy in the Curvaton field prior to its decay. So a quick review of the Curvaton model. In the Curvaton scenario, the inflaton still dominates the energy density and drives inflation in the exact same way as before. The new piece is that there's a subdominant light scalar field during inflation with a very simple quadratic potential. It's light, so its mass is much, much smaller than the Hubble parameter during inflation, and its energy density is much, much less than the energy density of the inflaton, so it does not affect the dynamics of the expansion. Both the inflaton and the Curvaton will pick up quantum fluctuations during inflation, and it's important that the amplitude of these fluctuations for the Curvaton be less than the background value of the Curvaton field. Now, outside the horizon, a perturbation in the Curvaton field and the mean value of the Curvaton field obey the same equation of motion. So here's the background equation and the first order perturbation equation. If you move outside of the horizon, this k squared term becomes negligible. And if you evaluate this v prime and v double prime for our simple quadratic potential, you see that this final term here has the same form for both fields. So since they obey the same equation of motion, their ratio is going to be conserved during and after inflation. So we can treat that as our conserved quantity in place of what we usually would use the curvature perturbation zeta for. After inflation, the Curvaton is still obeying its equation of motion. As long as the Hubble parameter is greater than the mass of the Curvaton field, the Curvaton is effectively frozen. When the mass becomes equal to the Hubble constant, the Curvaton will begin to oscillate in the bottom of its potential well. When it oscillates, the average value of its potential energy is equal to the average value of its kinetic energy. And that means that the average value of its pressure is 0. It's effectively behaving like matter, which means it's going to fall off as a to the minus 3. Meanwhile, all the radiation that's left over from the decay of the inflaton, which was the dominant piece of energy in the universe, is falling off as a to the minus 4. So as the curvaton oscillates, this is a numerical solution I pulled from a paper by Lingor and Venizzi. The curvaton starts out at its initial value, begins to oscillate, and then it will decay. While it's oscillating, omega curvaton can grow with respect to the radiation. Consider a curvature perturbation. This is our well-known friend zeta. We're used to zeta being conserved outside of the horizon, but that's only for adiabatic perturbations. Here we have a curvaton isocurvature perturbation, and that means that zeta will evolve. However, the curvature perturbation on slices of homogeneous curvaton and homogeneous radiation are still conserved, because the two don't talk to each other. And that means that the total curvature perturbation evolves between, initially, it's equal to the curvature perturbation in the radiation spring, because rho r is much, much bigger than rho sigma. But as rho sigma grows relative to rho r, it will approach the value of the curvaton curvature perturbation. So as this ratio changes, zeta evolves. Now, eventually, in the very early universe, the curvaton is postulated to decay. And the residual curvature perturbation it leaves behind is equal to some parameter r times the initial zeta on slices of uniform curvature density, curvaton density. This new parameter r is basically just 3/4 of the energy density of the curvaton over the energy density of radiation evaluated at the time of decay. So here we have different possible trajectories for the curvaton field. This is omega curvaton. It always starts at 0. It will grow while it oscillates, and then it will decay down to 0. And r here is increasing on these different trajectories as the decay time gets later and later and later. So we've seen how fluctuations in the curvaton field become curvature perturbations. The curvaton energy, which determines this zeta, is just its quadratic potential, and the energy is conserved as it oscillates, or goes as a to the minus 3. And that ratio of energy density perturbation is equal to the variation in the field itself over its mean value plus that quantity squared. And recall that this ratio is conserved outside the horizon. Now, we had those quantum fluctuations, as before. The reason why I said earlier we need those to be smaller than the mean value is we need this first term to dominate over the second term, because this is a Gaussian quantity, and this is not. And we'll talk a bit about non-Gaussianity of this model later. During matter domination, psi is just directly related to zeta. So we end up with a power spectrum of potential perturbations from the curvaton field. It's proportional to r squared times h over the mean value of sigma during inflation. That's what I mean by this star squared. Remember, this ratio, though, is conserved. Now, r is proportional to the energy density of the curvaton itself. So you pick up another 4 factors of the background value. And that means that this power has a very strong dependence on the background value of the curvaton field, which means this is how we're going to create our asymmetry. We're going to postulate the existence of a curvaton superhorizon fluctuation. And when you do that, again, you're changing the mean value on one side of our sky as opposed to the other. That changes the amplitude of the oscillations. This dependence is much stronger than we had before. There's no 1 minus n sub s parameter to suppress it. And you just end up with a power asymmetry in the curvaton power that's equal to 2 times the change in the curvaton across our observable universe over the background value.
Yeah, and I asked the same questions. You keep it by hand. It's not dynamical. Is it possible to have dynamically significant gradient like that?
So I guess I'm not entirely clear what you mean by dynamical. It's a structure. You're right that it's going to require a certain number of E-folds of inflation, that this structure was there.
No, so you have a background field sigma bar.
Mm-hmm.
If I put this field very squeezed initially by
Mm-hmm.
inflation, very soon it will be flat. It will be background. And given time patch, it will be just function of time, just slowly rolling. There will be no any features, no any imprinted structure.
So delta sigma over sigma is conserved outside the horizons.
I'm saying it doesn't exist at all.
It does.
No, there is a perturbative delta sigma.
Mm-hmm.
But what you say, you take sigma star and make it function of x. Sigma bar is function of x.
Mm-hmm.
You make background depending on the position.
Right.
And I'm saying it's not possible.
That's not good. Okay, then maybe we are just passing by hand. I'd like to talk about it with you later.
I have a bit different question. So, what makes the amplitude of the perturbation at this large mode in this model so much higher than on the shorter scales?
I'm sorry, say that again?
So you get perturbation across the horizon, which is pretty large difference, right?
Mm-hmm. Right.
So what's happening in this Curvaton model with the smaller scales?
So the small scales.
The amplitudes are somewhat half, is not one.
So the small scales are exactly what they're just oscillating in a different background value, and that's why their amplitude's different. I guess I maybe don't understand your question.
No, that's probably you do understand. So why do they oscillate in a different background?
Because this super horizon perturbation basically means that when we look out at different sides of the sky, we're seeing a different mean value of the Curvaton field at different locations. And that different mean value, the smaller scale oscillations, the ones we actually observed, are perturbations on top of that different mean value. And that's what's changing their amplitude.
Yeah, but I kind of don't feel what separates the scale. If you go from long waves to the short waves, why there is a sharp change in an amplitude?
I don't think there's a
exactly why it's not consistent.
What you mean? Where does this come from? Why is this so much bigger than this?
Yes.
I'll talk about that at the end. Some origins that we want to have for the supermode and where we think it may come from. So this power asymmetry that you pick up from the Curvaton, what does it look like, and what are the constraints on it? So we have to worry about the CMB constraints again. This Curvaton supermode still will generate a superhorizon potential fluctuation, but it's going to be suppressed relative to what we had before. It's suppressed by this factor R, which is the fraction of energy density in the Curvaton just prior to its decay. Another key difference to what we had before is that the potential here is not just proportional directly to delta sigma over sigma bar. It also has this term squared, which means if we start out with a sinusoidal perturbation in sigma, we're not going to end up with a sinusoidal potential perturbation. So we start off with our Curvaton supermode. The temperature anisotropy, again, we can expand it in powers of k dot x, but now, instead of just having a sine and a cosine here, we have these complicated relationships as sine omega minus the ratio of the amplitude to the background value times cosine 2 omega here in case it's too faint to read. We have these complicated relationships on our location, the phase of our location on top of the sine wave. And that means that the constraints put on by the quadrupole and octupole depend on the phase, depend on our location on that sine wave. And I just plotted here for a fiducial order unity superhorizon perturbation with some realistic value that we would like for the asymmetry for the variation across our observable universe. What is the upper bound on R for different phases? And you can see that the red is excluded by the CMB quadrupole. That takes out most of the region here, except for this very strict upper bound. However, there are some sweet spots where the quadrupole will vanish. In those regions, it's the octupole in blue that are going to give you a constraint. And then finally, in yellow here, we've got places where we're on the maxima or minima of the potential perturbation, and so there is no delta sigma. It's not consistent. So the quadrupole, we chose to evaluate it at phase equals 0 because that's basically, a general feature here for the constraint. Most other phases give similar bounds. And the quadrupole constraint here, the key difference is we now have this free parameter And so instead of this ratio here is related to delta P over P, but now we no longer have an absolute constraint on delta P over P. It's multiplied by So we have some wiggle room. Another free parameter we're going to put into this model. Remember that both the curvaton and the inflaton may contribute to the power spectrum. Root mean square fluctuations from quantum fluctuations are put both in the inflaton and the curvaton fields at the same magnitude. Now those quantum fluctuations become potential fluctuations in two different ways. The inflaton is different because it's dominating the energy density, so you end up with a different formula. However, it's proportional to 1 over epsilon here. This one's proportional to a squared over sigma bar squared. So you could conceivably have a mixed inflation model where the new parameter is the fraction of the power from curvaton oscillations over the total power from both inflaton and curvaton oscillations. And this parameter C is determined by the three parameters I discussed before, the mean value, the R value, the ratio of the energies, and the slow roll parameter epsilon. Now notice that although this combination is always very small, we don't have a lot of constraint on the background value of the curvaton field. So if the curvaton field is much, much less than the Planck mass, it's conceivable that this quantity is big, and you have C near to 1. If the curvaton value is instead comparable to the Planck mass, you end up with C much, much less than 1, and the inflaton's perturbations will dominate. A key point I want to mention is that when you're making the curvaton fluctuations dominant over the inflaton fluctuations, you're pushing the tensor fluctuations even lower because the tensor fluctuations are always smaller than the inflaton fluctuations. And so if you're pushing the inflaton fluctuations down, you're taking the tensors down with it. And that means that the tensor scalar ratio is very much reduced in these models. It's proportional 1 minus C. So in the limit that all the power comes from the curvaton, there are no tensors. So how can we constrain our curvaton model? The curvaton and the inflaton both contribute to the power in this parameter C. We want the fluctuation in the curvaton field to be at most order unity across our observable universe. Otherwise, it just starts climbing the other side of its potential well, and that doesn't bias anything. So this constraint leads to a strict lower bound on C that rules out the yellow here. So here I've plotted R and C, our two parameters, for two different fiducial values of the power asymmetry. The 20% that we want to explain, and for comparison, a smaller asymmetry, 5%. So the yellow is excluded by this simple lower bound. The red is excluded by the quadrupole constraint I mentioned before. The blue is the non-Gaussianity. So remember our form for the potential. It's actually a Gaussian fluctuation, this delta sigma, plus a Gaussian fluctuation squared. That means it's a very convenient parameterization of the usual F and L parameter, which is inversely proportional to R and proportional to C squared. It's diminished as more of the fluctuations come from the inflaton. And using our upper bound from WMAP of about 100, that rules out this blue area. Now notice this is independent of the asymmetry. It's just a feature of the curvaton model itself. And then we see that there's great rejoicing in the halls of Caltech because there isn't a loud window here. And this is a log plot, so the window is not even as small as it appears. This combination of parameters, R over C squared, is bounded from below by the non-Gaussianity and from above by the quadrupole. And now we come to the deal breaker. This window here closes completely if F and L is constrained to be less than 50. So this model makes a definitive prediction about what the measured non-Gaussianity will be that's very testable by Planck in the near future about whether or not the CMB data is consistent with such a large value of non-Gaussianity. So coming to some origins of the supermode. Our first idea was hopefully maybe the supermode could just be an abnormally large quantum fluctuation. It was just a fluke. Well, then we asked how large would it have to be? So at some point in inflation, the super horizon mode was a quantum fluctuation that was just super big, and it left the horizon. And then all the other perturbations happened on top of that abnormally large perturbation. Well, the power spectrum from the quantum fluctuations, we've seen it before. It's a fraction c of the total power spectrum, and that's been measured. So this gives a quantitative evaluation of the perturbation size. And when you consider this root mean squared perturbation and multiply it by our asymmetry, here's the asymmetry term, here's the evaluation from just the observed power spectrum. And when you input several things, you end up with a strict upper bound of 1/5. So what I inputted here is just the power asymmetry that we wanted to observe, F and L less than 100, and the lower bound on C that I mentioned before. And so what you see here, given that the mean values cancel, is that the variation in sigma across our universe is bounded to be 5 times the quantum fluctuation value. The amplitude of the supermode must be even larger still. So the supermode would be at least a 5 sigma fluctuation, and that's highly improbable.
Let's at some level, ray event in one Gaussian map, you would like to explain the ray event in another, maybe not Gaussian, but
exactly. No, and that's why we reject this idea, because it's more unlikely that this thing be a quantum fluctuation than it is that the asymmetry could just be a statistical fluke. So some other more exotic ideas that we'd like to throw out there for origins. This could be a signature of the so-called Curvaton web, that during inflation you have oscillations of the Curvaton around its 0 point. And these oscillations lead to cells that are bigger than the observable universe, where the Curvaton within each cell is frozen at some background value. But between these cells, you have domain walls. And in Linde and Newton's original paper, they even point out that if our observable universe is inside one of these cells, and it's nearby a domain wall, what you would see is a power asymmetry. You'd see higher amplitude fluctuations in one half of the sky than the other. I don't know if they weren't aware of the observed asymmetry or they didn't want to mention it. But it is a mechanism for generating the asymmetry that we've seen, and with all the constraints I've shown you, it does actually work. If we don't want it to be a signature of the Curvaton web, then it could just be a pre-inflationary remnant that was outside of the horizon before inflation. Inflation shrinks the horizon, it re-expands it, and now it's again right outside our horizon. The constraint here is that this wavelength can be about 10 times our observed universe. That would, of course, require certain limits on the number of e-folds of inflation, but this could be a signature of some pre-inflationary remnant. Finally, there was an earlier question at the beginning of the talk that I want to touch on briefly about what scales has the asymmetry been observed on. It's been detected for L between 5 and 40. There are some more recent analyses that see a reduced asymmetry for L greater than 100. How much it's reduced and at what sigma is it ruled out is a little ambiguous at the current time. But there is mounting evidence that this asymmetry does have some scale dependence. It does go away at smaller scales. How could we make our asymmetry disappear on small scales? Well, recall that only the Curvaton fluctuations are asymmetric. The inflaton perturbations are still statistically isotropic. So we can introduce scale dependence through this ratio of power from the Curvaton to power from the inflaton in the Curvaton. And 2 ways we're thinking about about doing that. The first is the simplest, just inducing an extreme feature in the potential for the inflaton. The way you do that is, again, looking at that form of C. Remember, it was dependent on epsilon. So if epsilon, the slow roll parameter, had some kind of break or feature in it, you could decrease epsilon, which would rev up the inflaton perturbations and decrease the ratio of power coming from the curvaton, as we desire. Now, revving up the inflaton perturbations would lead to an increase in the power spectrum itself, but you can adjust for that by decreasing the potential of the inflaton at the same time, and that will keep the total power roughly constant. So we're talking about a feature that looks like this. It goes from a relatively high epsilon to a very, very low flat epsilon, and at the same time has a drop in the potential. Now, I personally think this is rather hideous. So another idea that we've been thinking about is it is very easy, and some would say possibly natural, to get isocurvature modes from the curvaton. If the curvaton were to decay into a different mixture of matter and radiation than the inflaton did, or if the curvaton were to decay after dark matter had already decoupled, you would end up with isocurvature modes. And isocurvature perturbations contribute more on large scales to the CMB anisotropies than adiabatic perturbations do. And remember, we don't need a lot of them. We only need about 10% for the 10% modulation in the power. And that's about where the current upper bounds are. So this is work that we're in progress right now of looking at models of isocurvature fluctuations to see if we can make the asymmetry disappear on small scales without resorting to a feature in the potential that looks like this. So to summarize briefly, there is a power asymmetry in the CMB. It's present at about the 99% confidence level, and it's detected on large scales. A superhorizon perturbation during inflation could generate exactly such an asymmetry. It also generates large-scale CMB temperature perturbations, though. There's no dipole, but the quadrupole and octupole set very strict limits on the amplitude of these perturbations, and that's discussed in the second of the two preprints I mentioned. An inflaton perturbation is ruled out by these constraints, but a curvaton perturbation is still a viable source of the observed asymmetry. It satisfies the non-Gaussianity constraints and the quadrupole constraints. Some features of the curvaton-generated power asymmetry. It's not a quantum fluctuation, so you need to appeal to something more exotic to create it. The produced asymmetry in the simplest model is scale invariant, but it is possible to modify that either by appealing to breaks in the potential or to isocurvature modes. Two observable effects of this mechanism is it suppresses this tensor scalar ratio. Detection of gravity waves in the CMB, B-mode polarization, wouldn't rule this out, but it would create a fair amount of tension in terms of measuring 1 minus C. What would rule it out is a measurement of the inflationary consistency relation, because the spectral index for the tensors is totally unaffected by the presence of the curvaton. However, a more immediate test will come in the form of non-Gaussianity, because Planck will be able to measure conclusively if F and L is greater than 50. And this mechanism for generating the asymmetry demands such a high level of non-Gaussianity. Okay, thank you very much.
So I have problems with making such inhomogeneities. I don't see any viable mechanism to make it.
For making it.
Including the Curvaton scenario.
What?
I don't see how we can get a gradient across of the horizon.
Because it would get stretched out, you're saying.
Actually, I don't see. This problem has been on the table for a long time. I don't have to see if you could, when the days of the really large dipole were in place and all that. The only way is this really remarkable feature in the V, the potential, and that's what is being required here I mean, your other mechanisms are interesting, but I actually think that you're going to have to come down to a big hit with the potential that's got a feature just sitting outside of the horizon that has that K modes. It's like making a mountain of power.
Right.
The trouble with mountains of power is that it's pretty difficult to get the quadrupole suppressed like it is. You know, the optimal power spectra, they always try and go down, not up. Right. And so here you've got a battle on your hands.
Exactly. That's
especially if you're using Curvaton issues, because as you pointed out, the curvature mode has this big amplifying factor.
Exactly.
Which is a factor of 6 relative to the naive sense, and it's huge. And so the real problem will be, because you haven't actually taken this into account, but to actually deal, I mean, you've sort of done it by looking at quadrupole and octupole, but that whole structure moving into somewhat higher L's is actually where I think the biggest constraints come from with this class of models. But it's not impossible, it's just that it's difficult.
Well, you have to leave.
Yes, but
it's like a huge domain wall. You have to leave nearby a huge domain wall.
Well, no, that was an interesting possibility here. It seems to me that that's actually where I would put some attention.
Yeah, but it's different model. It's not Linden Punch model.
No, I know. But,
no, outside domain wall, when you see a tidal, when you see gravity, linear gravity.
No, I mean, to get a mode like that, that's
Yes, the domain wall is already there.
But since it was difficult, you better be kind of in a more probable scenario than 3 sigma in whatever measure. Because,
well, of course, that's the other
right?
difficulty, the
So
fine tuning to keep it just what you need. But on the other hand, you know, we're dealing with fine tuning all the time.
So I have a question to locals in the experts. What is the status of asymmetry from W5?
This is 5 to 40. Does that change?
Right. And 5 to 40 is pretty. There has been a more recent analysis. Barstow-Liu looked at this asymmetry using WMAP5 data and found, not surprisingly, because like Mark pointed out, these multiples haven't changed between, first year to 3 year to 5 year that much. And it's there at the exact same level in the exact same place. He actually looked a little more carefully also at different multiple regions, and that's why I cited him as one of these studies that show that it might be falling off at higher multiples.
Do we have a feature in the clusters motion? Like in Erickcek?
That's a little difficult to look for.
Not according to Kaslinski.
Oh, the cluster motion, like this dark flow you're asking about. I was kind of excited when I read that. I immediately looked in Scale if it was aligned with the asymmetry. It's most definitely not. So that's not the same axis, unfortunately. In terms of looking for this asymmetry in large-scale structure, you're kind of battling the fact that, for instance, in the model that we proposed, if your sphere of observation is closer in, as it would be if you were looking at large-scale structure, you're seeing less of the superhorizon perturbation. So the asymmetry you'd expect to see would be suppressed. So that makes it more difficult to see on large-scale structure. The other difficulty is there aren't a lot of full-sky structure surveys. Structure surveys are done by telescopes, which by definition only have limited viewing of the whole. I don't think there's a single data set that's the entire sky. But it's something to look into, and I would be interested to see.
So on the other hand, although you are limiting yourself to a smaller region, as you said, you may be sensitive to the gradient. And you don't.
Right.
So the significance of this depends on the range of wave numbers that are found to be asymmetric.
So the different likelihood contours that you find, yes, there are different likelihood contours for A depending on which range of multiples you look at.
And so what are the prospects for increasing that range of wave numbers?
Increasing?
The range of wave numbers that you can test this.
And like I said, some of those more recent studies. Some of the more recent studies, in particular this recent paper by Barstow-Liu, looks up to 80. Some people have looked at the first peak to see if the first peak is asymmetric or not. Again, there seems to be mounting evidence that it does fall off at smaller scales. Exactly how fast, exactly what sigma, what are the upper bounds, those seem to vary wildly between analyses. But a picture is emerging, and I hope that some more CMB data analysis jocks will come in and clear up the situation on smaller scales.
Any alignment with the axis of
Not aligned with the axis of evil.
And the ecliptic?
And the ecliptic, it's actually, that's the closest thing it's aligned to. It's about 20 degrees away from the ecliptic, which of course is interesting, but I have talked to some solar system scientists about this, about what mechanisms could you imagine to create CMB asymmetry, roughly aligned with the ecliptic. And that's an even more difficult question. You wouldn't expect to see anything in the CMB that's aligned with the ecliptic. But yeah, that's the closest thing in the sky that this asymmetry is aligned to. It's about 20 degrees off the ecliptic.
So why don't we, since we're done the time, why don't we have the rest of the talks so the cookies upstairs and the next speaker?